Hey everybody, we're going to take a look at section 3.9 next, using implicit differentiation. But first, let's take look at one example of finding a second derivative with implicit differentiation. That's the one thing that we didn't quite do last time. So I'm going to do the same thing where I'm just going to have to be typing here, and let's take a look at one of these problems. So last time we talked about how implicit differentiation is nothing really more than remembering that y itself is a function and that we need to take the derivative of both sides of the equation. Well, for finding the second derivative, we're going to have to do that twice. Okay, so the only extra tricky thing here is beyond the fact that the first derivative is usually a little bit more complicated than the original equation, so the derivatives are going to be a little bit harder to deal with sometimes. But the second part of this is that if we have a formula for the second derivative, we don't want there to be a y prime in that formula, because otherwise we have to go through the whole process of figuring out what y prime is and remembering what it is to work with it. So as you take that derivative, you are replacing y prime with whatever you found in the first step, and then of course simplifying as much as you can. All right, so taking a look at the example here, we're working with 2x minus 3y is equal to xy. So going through and trying to take the derivative of both sides, derivative 2x, not a big deal, that's just 2. When we're taking the derivative of negative 3y, the negative 3 is a constant coefficient that stays put. This is not the chain rule because it's just a coefficient times y. So this is just going to be y prime. There's no extra y involved there. And then on the other side, we have to make sure that we're using the product rule. So the derivative of x is 1 that we have to multiply times y. And then we have to add on the derivative of y, which is just y prime, that we have to multiply times x. Okay. So that's our first step. Now it's just a matter of moving things around so that we get this solved for y prime. So I'm going to go ahead and subtract the y from both sides, add the 3y prime to both sides, and that's going to leave us with 2 minus y is equal to y primed x plus 3y primed. And as we saw previously, now we just need to factor out that y prime. And as always, if you can do this algebra without writing out the extra step and kind of doing some steps mentally, absolutely be my guest. But just showing step by step, we factor out the y prime. Now that y prime is just here once, divide both sides by x plus 3. So we're going to be left with the fraction 2 minus y divided by x plus 3. Okay, so that's a very quick review of the implicit differentiation that we did last time. Now we need to take it a step forward. And so once again, we're going to end up taking the derivative of both sides. The derivative of y primed is, forgot the equation, y double prime. And now we have to go through and use the chain rule. So not the chain rule, what am I saying? We have to use the quotient rule. So we know that the quotient rule is going to give us a fraction. In the numerator, we have the derivative of the numerator of our original fraction. So we have to take the derivative of 2 minus y. The derivative 2 is going to disappear. Think of the negative as a negative 1 coefficient, so that negative sign is still there. And the derivative of y is just y prime. And we have to multiply that times the denominator. And then we're always subtracting our quotient rule. The derivative of the denominator is just 1, right? Derivative of x is 1, the derivative of 3 will disappear. So we're just going to have a 1 there that we have to take times 2 minus y. And in the denominator, we always just get whatever was in the denominator, but now it's squared. Okay, so that's the implicit differentiation part. We just took the derivative of both sides again, but as we mentioned up above in the instructions, you cannot leave this y primed in here. Okay, and so maybe there are certain circumstances where it's not a big deal because you have all the information right there. But if you told somebody, hey, the second derivative of this formula, sorry, this equation is this, then it's going to force them to have to go back and figure out what y prime is. Okay, and so all we're going to do here, of course, if it's paper and pencil, it's a little bit more annoying to have to write this all out, but I'm going to, oh my goodness, I'm just going to cheat here and do some copying and pasting. We know that y prime is 2 minus y divided by x plus 3. So we're just going to come in here, replace y with, y prime with 2 minus y over x plus 3. Okay. And it doesn't always work out as nicely as this. I kind of picked a nice example to make sure that we weren't going too far here. But you can see in this particular case, that x plus 3 in the denominator there is going to cancel out with the x plus 3 in the numerator, or just the whole number here. So these guys are going to cancel out. Do make sure that you distribute the negative sign to both the 2 and the negative y up there. So what we have at the moment is still working with a whole fraction for the whole piece, but at the beginning, we're going to get a -2 and a plus y. Okay, so again, -2 and the two negatives make a plus y. The x plus 3 is canceled out. And if I distribute that -1 over here, I get another -2 plus y. The denominator is still going to end up being the x plus 3 squared. And then finally, obviously just go through and collect your like terms. You don't want to leave it crazy like this. So I'm going to, again, want to cheat and do some copying and pasting here. But if we combine our like terms there, that's nothing more than 2y's, and -2 minus 2 is -4. And then we have said in the past that sometimes it is nice to have it in factored form. You can see immediately, even if I factored out the 2 as a common factor, you're not going to get anything that cancels, and it's not particularly easier to work with. So that's one of those times where it's kind of an optional step. You can do it if it feels like it's something that's important for you to do, but it's absolutely not necessary there. And so that's just a quick idea of what it looks like to take the second derivative using implicit differentiation. Right, so now that we've kind of warmed up on that and you've seen an extra example dealing with the implicit differentiation, we're going to take a look at section 3.9, which is technically all about the derivatives of logarithms and exponentials. But this is really nothing more than using the implicit differentiation that we just talked about, along with some rules from algebra to help ourselves out. Okay, so in general, you have to remember all the different differentiation rules that we've talked about, but the two big ones here, the chain rule, implicit differentiation, do make sure you still remember your product and quotient rules. They might still come up from time to time. But the important tools from algebra that we're going to be using here, the first one is generally called the power rule for logarithms, and we've talked about this one before. It doesn't matter what type of logarithm you're dealing with. Here, we're almost always dealing with natural log, so that's how I'm going to write it. But if I'm taking the natural log of something raised to some sort of power, that is exactly the same thing as multiplying that exponent times the natural log of what we started with here. So we've seen this a couple times before, where basically the exponent just comes out as multiplication. You leave the rest of the natural log itself. Okay, so you'll see when we put all this together why that becomes an important thing to remember, but that is certainly something that we're going to use a handful of times here. Regarding the inverse property, there's a couple of inverse properties out there, but just bear in mind that if you're working with E and natural log, come on now, those are opposites. So if I take E of natural log of X, that is absolutely just going to let me write it backwards. It's just going to give you an X. So we're kind of used to, in previous ideas, used to starting with this and working backwards and replacing it with X. Seems a little bit weird here. We'll see why in a moment, but we're sometimes going to replace either a number or a variable with just E raised to the natural log of whatever that number it was that we started with. Okay? And again, it doesn't have to be just a number or a variable. You can have full-blown expressions here. Not that this would come up too terribly often, but you can have something like 2x minus 1. And if for whatever reason you wanted to write that in terms of E, you'd have to raise it to the natural log of, excuse me, the 2x minus 1. So those are, again, identical expressions because E and natural logs cancel themselves out. Right, then the change of base formula is something that you may or may not have used often previously. But here, I'm just going to give it to you. It doesn't matter what logarithm or what base you have in your initial logarithm. You can always change that to a natural log problem, which is good for us because that's the type of logarithm we're going to be most using here. But log base b of x is the same thing as the natural log of x divided by the natural log of whatever that original base was. Okay, so this is something that we're going to use so that we can create one single rule for natural log when we're working with derivatives, and any other logarithm, we can just convert it and then take the derivative. Okay, and so that's kind of what all of this is about. Even though I haven't done any examples yet, we're going to convert things that are trickier to work with to things that are easier to work with. And here, I know that x and 2x minus 1 are not hard to work with, but we'll see how sometimes it's easy to work with e than some other relationship here. Right, so let's take a look at putting this all together. And so if we're using implicit differentiation to prove that the natural log derivative of the natural log of x is 1 over x, which is something that we brought up, excuse me, um, I lied. I was going to bring that up, but then we did not meet after spring break. So this is, I guess, the first time we've seen the derivative of natural log. What we're going to start with here is just the idea that we don't know how to work with natural log. It's not like there's any sort of rule here that says, hey, we can take this and come up with 1 over x. But hopefully we remember, let me just write this out, that if I'm looking at the function y is equal to natural log of x, this is also kind of an inverse relationship that I didn't bother to write up above. But if y is equal to the natural log of x, that means that if I take e to the y, that's going to give me x. And so for some of you that might look familiar. If not, let me just take a step back here and we can stop with that. But you can really just say, well, I'm just going to raise e to the left-hand side and raise e to the right-hand side. And we just got done saying e and the natural log of x are going to cancel out because they're inverses. And that's how you end up with e to the y is equal to x. And so that becomes important simply because now we know how to take the derivative of e. We know how to use implicit differentiation so we can handle the y there. So we go through and do it. The derivative of e to the y is, first of all, e to the y, because the derivative of e is kind of itself. But remember the chain rule here, we also have to take the derivative of the exponent, and since the exponent contains a y, we do get that y prime, and the derivative of x over there is 1. Okay, so if we're solving for y prime, that's super easy. I just divide both sides by e to the y, and we have the equation solved for y prime. And then finally, this is a lot like the second derivative we did before. We could leave our answer like this, but everything that we're dealing with up here is in terms of x's. So we probably don't want to leave this as e to the y if we can manage. Okay, but all we're going to do is take a look at this last little piece of information here. This is kind of where we started, but e to the y absolutely is equal to x. That's what we started with. This has to be true for any of this to make sense. So the last step is just making that quick replacement, that y primed is going to be 1 over x. And then finally, just keep in mind that y was, again, up here, y was equal to the natural log of x. And so what we've just accomplished is actually finding the derivative of the natural log of x. Right. So again, you're kind of going to see this in section 3.9, 3.10, and 3.11. There's a whole lot of implicit differentiation going on that's really useful as you derive and come up with these other properties. Okay, so this I should have made sure is absolutely clear. This fact right here, that is crucial for you to memorize. Okay, you absolutely need to memorize that the derivative of natural log of x is going to give you 1 over x. If you read through the textbook, it'll give you formulas for finding the derivatives of other types of logarithms. It'll give you formulas for finding other types of exponentials other than e to the x. And there's a handful of problems where it's even going to give you some things where you have an x both in the base and in the exponent. So kind of a hybrid problem that we haven't seen before. But all of these down here, it's not really necessary to memorize, hey, this is the formula for this type of exponential, or this is the formula for that type of logarithm. All we're going to do every single time is just rewrite the problem so that we're either dealing with e raised to some exponent that we know how to take the derivative of, or we're going to rewrite our logarithms in terms of natural log because we know how to take the derivative of a natural log. Right, so we're going to work through, I guess, 5 examples here. Maybe there's 6. There's 6 down there. And these are all going to be pretty much the same. Okay, so in this first one, the first thing we would do is say, well, we don't have any idea of how to take the derivative of this. It's not a power rule because a power rule has a whole number in the exponent. It's not allowed to have a variable up here. It's certainly not an exponential rule because I have an x in my base. And so right now we don't have any rules to work with. Okay, so this is where we're going to take it and rewrite it in terms of e raised to the natural log of whatever it is that we're working with. So in this case, what's kind of crazy, but we end up with an e raised to the natural log of x dx, because again, the natural log and e would just cancel out, so we haven't really done anything there. And now we're going to go back and use the power rule for our logarithms that say that we could take the exponent from the variable and write it as multiplication in front of the logarithm. So we're still working in the power of e, but now instead of natural log of x dx, we can take that exponent out as multiplication and multiply that times natural log of x. Okay, and at this point, it's just a chain rule. Okay, so this is going to kind of look like implicit differentiation just because of how I chose to write the initial equation. So when I take the derivative, I am going to get just y prime there. But using the chain rule, the outer function is e, right? Because x natural log of x is inside the function e. So when I take the derivative of e, nothing changes, right? So we're still going to get e to the x natural log, goodness, of x. That didn't change. But now we also have to make sure that we're multiplying by the derivative of the exponent. And I went ahead and put a parenthesis there because in the exponent, we can see that that is multiplication. We're going to have to use a product rule, so it's important that we write this out as a product. Okay. So looking at that exponent, the derivative of x is just 1 that we have to multiply times the natural log of x. And then add on the derivative natural log of x is 1 over x. And we have to multiply that times the first function, or just the x. Okay. And then the last step here is nothing more than making it a little bit tidier. So we're going to go back and recall that x to the x is the same thing as e x to the natural log of x. We just rewrote it. So that e x natural log of x, I guess you can leave it, but just so we can see it a little bit easier, we can replace that with x raised to the x power. And then the rest of this is nothing more than just a quick simplifying. 1 times natural log of x is x. 1 over x times x is 1. Okay. And so that is the derivative that we get when we're using our exponent rules and the information we know about e. Okay, so I started with this one just to show that sometimes you don't have a choice. There's no rule that's out there that says, hey, this is how you take the derivative of something where there's an x in both the base and the exponent. It's literally just know your exponent rules so that you're able to rewrite things and do it. And if you're going to need to do that anyway, you might as well go through and do that with any problem that has any sort of weird exponent. Just start another page. So again, you can look at the textbook, and the textbook's going to say, hey, there's a formula for this. But instead of doing that, let's just get in the habit of rewriting this. We know that we can take e and raise it to the natural log without changing anything. And we're taking the natural log of 3 to the x. And then this is just the exact same pattern we had before. It's just going to be a little bit easier. You still are allowed to take the exponent on the 3 and write it in front of the logarithm using the power rule for logarithms. So we're going to have e raised to the x times natural log of 3. And then when you end up taking the derivative, it's just a chain rule again. Okay, so once again, we have e raised to a power. So the e raised to a power part, that does not change whatsoever. And then we have to multiply that times the derivative of the exponent. Now it's still multiplication here, but this time, natural log of 3, that's just a number. Okay, so we're not going to have to use a set of parentheses there. If I take the derivative of x times the natural log of 3, natural log of 3 is now just a constant coefficient. So the constant coefficient stays. And when I take the derivative of x, it turns into a 1. Okay, so again, if you're a memorizer, I guess you can kind of memorize the textbook formula, but it doesn't take all that long to do a quick conversion. And if it's something that you're doing anyway, you might as well take it a step forward and just kind of do it with almost every problem at least. The only thing I'm going to change here is just going back and doing the same thing we said before. E to the x times natural log of 3 is really just 3 to the x. So if you want to write it more in context of the original problem, this is just 3 to the x times the natural log of 3. Okay. So again, it's a little bit longer to do it this way than to memorize the rules, but at the same time, it doesn't take that much longer. And these types of exponents don't come up all that often, right? So it's not something that's maybe worth you memorizing if you can go through and do it in this sort of context, right? So the only new problem we need to talk about then is working with the logarithm base 5. So we mentioned this earlier that if we have something in a different logarithm, we can convert it to the natural log by taking the natural log of x in the numerator and then just dividing by the natural log of whatever the base is. Okay, so this one's going to go even faster than what we just did a moment ago. There's nothing to do here other than realize, I guess I'll write it out nicely, to realize that that natural log of 5 in the denominator, that is just a constant coefficient. It's a weird way of writing it, but you can write 1 divided by natural log of 5 times natural log of x. And as long as you understand that this 1 over natural log of 5 is a complicated, crazy coefficient, but it's a constant coefficient nonetheless, now it's just a matter of saying, well, constant coefficients stay exactly as is, and the derivative the derivative of natural log we learned earlier is just 1 over x. And so I personally would tend to leave the answer like this, but I know the textbook likes to combine your two fractions together. And it'll write it as 1 divided by x times the natural log of 5. Always writing the natural log last so it's clear where the natural log ends and starts. Okay, so again, kind of two different ways of writing this out this time. Both are acceptable. Right, so the rest of this is really just tying together the logarithm and exponential rules with more complicated problems. I am going to pause the video for a moment here. This went longer than I anticipated, so I'm going to stop this one, start back up in a minute or two with the rest of these.